a very good afternoon to all of you. So today is the week three of our live session uh, for the NPTEL course Ultrafast Laser Spectroscopy. And here today, as I see, no one has joined yet, but I'll wait for a time of around 2 minutes so that at least few people can join so that I can start the session. Yeah, so I think it's 3-2 and no one has joined till now. And although I'm signing in through a different device so that I can let other people join because once I present it will be an issue. Yeah. So here we'll start. So first of all, uh, in this course we have since now we have learned different techniques to learn how to study the different fluorescence decays and curves, and what are the different experiments that they have done, including steady state fluorescence studies to TCSPC, which is time resolved single photon counting technique. Now in this week we'll be study we had discussed a different technique which is called fluorescence optical gating, known as fog, and different detectors which are related to it and how the technique works, its instrumentation, and we had also gone through the lab work, how it is done in the lab, or how the apparatus or the experiment is done in the real. Now since it's already 3-5, I prefer we'll join I'll start the presentation and start discussing the questions. So first of all, this course is taught by Professor Anindya Datta, and I am a teaching assistant, Nikita Mahajan, for this course. So today is the third live session for problem solving, which involves the questions of week three, and here we'll be discussing different questions. So the first one is suppose the wavelength of a light obtained upon mixing the two beams of light with the wavelengths of 490 nanometer and 800 nanometer is. So somewhat this question actually is related to the fog instrument only, where initially what they do is like the up conversion, where the two wavelengths of light they just sum up. So in order to understand that question, although later on we'll be discussing the whole instrumentation, the setup, and also like what are the um, things we need to take care of while doing the experiment, and the other what are the different parts of the instrument and what are their functions. So first, with this question, we'll starting with this question. First thing will be like, suppose in a system you are given two wavelengths which are like uh, okay, which are like omega. Just a second. Yeah. So first, there are two wavelengths. Say it is lambda 1, whose value is 490 nanometer. The second one is lambda 2, whose value is 800 nanometer. Okay. Now normally if you do a calculation, what you will do is, like if I say you that you have to calculate the wavelength which is obtained upon mixing these two beams. So normally we think it would be as lambda 1 plus lambda 2. So if it is like 490 plus 800, then what it will be? It will 800, so it will be around 1290 nanometer. Okay, just a second. Okay. So basically, in this thing, if suppose if you sum up a light of 490 nanometer and 800 nanometer, anyways you would get the light which has a wavelength of 1290 nanometer. Why? Because these two light beams which you are trying to merge, they these two wavelengths, these are lower than that. And anyway, if you add two energies, suppose you add E1 and E2, like if you talk wavelength in terms of energy, the third energy, if you add up, it will always be greater than the first two. And if you think of the sum, that is 1290 nanometer, then it is in, just a second. Yeah, then it is no way the energy, the third energy. Then in no ways the third energy will have the third energy will be greater than the first two energies if the wavelength is 1290 nanometer. I suppose you got my point. Since energy and wavelength have an inverse relation, now suppose I add these two wavelength and get a third wavelength. And what about this wavelength? If the wavelength is high, the energy is low. But if you talk about these two wavelengths in terms of energy, what it will be? Like E1 and E2 you add and you get E3, which is still lesser than the E1 and E2. So this will not be the case anyway. First of all, what the case would be is that the total energy that comes should be greater than these two. Okay, so basically in order to solve this question, this is the mistake which most of the people will do. But in order to solve this exactly, or in the correct way, we have to think of these values in terms of frequency, or say energy. So first of all, we'll convert these two in terms of energy, and then we'll calculate the value of wavelength. Now suppose E is equals to H nu. We are well known with this relation, or we can say E is equal to H c by lambda. Okay. Now H is as usual the Planck's constant, c by lambda. Now if you want, what do you want to do is E3 is equals to E1 plus E2. Got it? So E3 will be anyway Hc by lambda 3. Okay, we'll denote it with 3. The second one will be Hc by lambda 1, and the third one will be Hc by lambda 2. Okay. Now Hc will be common, so it will come to be like Hc upon, like 1 upon lambda 3 is equals to Hc common 1 upon lambda 2 plus 1 upon lambda 1, and then like these two will be cancelled to each other. Okay, now we'll calculate the relation. So for this I think I need to erase a bit, so that yeah, or else it would be better if we go on a blank page. So first of all, what we did was E3 is equals to E1 plus E2, and then it is equal to HC 1 upon lambda 1 plus 1 upon lambda 2, and it is equal to HC 1 upon lambda 3. And then what we did was we cancelled these two, and also like 1 upon lambda 3 is equals to 1 upon lambda 1. Now say like as far as what I remember from the reading, lambda 1 was 800 nanometer, or say 490 nanometer. We can just change the value, like interchange the values, and this is 490. Now when you add both of them up, okay, so it will be 490 plus 800 whole upon 800 into 490. Now I'll do the calculation in the using a calculator, so that we get a fast reading. So it will be 490, 800, okay, and 90 plus 800. Yeah, so it will come to be like it will be as 1290 whole upon 39200 is equals to 1 upon lambda 3, and therefore lambda 3 will be equal to 39200 whole upon 1290. Yeah, so here my value is coming up to be around 303.8 nanometer. Okay, so yeah, now this is how we could get the answer of this question, and it is around 303.875 nanometer. I suppose in since like this is an easy question, which like no one would have doubting, or like maybe we should try one more question related to this, where we'll put different values of wavelengths, and just try it a bit once more. So here like just I'm keeping the value of light to be for say, okay, I'll go on the last page. Suppose I keep the value of lambda 1 is equals to lambda 1 is equals to 400 nanometer, and lambda 2 is equals to 790 nanometers. Now, when you sum them up, just find the value of lambda 3. So, as usual, we'll what we did, we'll do in a bit short way, like 1 upon lambda 3 is equals to 1 upon lambda 1 plus 1 upon lambda 2, and therefore 1 upon lambda 3 is equals to 1 upon 400 plus 1 upon 790, or say I kept it to be 780. Here also I correct myself. uh, it is it will be 780 nanometer, and here also it will be 780 nanometer. Okay, now again we'll do the same maths. 1 upon lambda 3 is equals to 780 into 400 whole upon 7, sorry, yeah, this is wrong actually. 780 plus 400 is equals to 780 into 400. Now this is correct. So it will be 780 into 400 is equals to 312,000, and 780 plus 400 will be 0, 8, and 1180. Now 1 upon lambda 3 is equals to 1180 upon 312,000. In order to calculate lambda 3, we'll again take the reciprocal. The third wavelength will be equal to 3,12,000, that is upon 1180, and this comes, here comes the value. So it will come out to be 264.406 nanometers. Yeah. Now see, here what is the relation of unit? Here the unit was nanometer. Here also the unit was nanometer. Or say it here the unit would be 1 upon nanometer, or say nanometer inverse, and when we take the reciprocal, finally what we get is the reading in nanometer in um, it will be finally in nanometer only. Now there is one more thing, like suppose I say you that here I have given you the relation. Okay, here I have written something wrong. Yeah, so if I have given this wavelength, or instead of wavelength I have given you the wave number. Okay, so if I give you a wave number, say uh, it instead of this it is 1 upon 780 nanometer, so it would be, and from nanometer we have to convert it into centimeter inverse. That would be, yeah, so it will be around somewhere around, say 12,000 or 13,000. So the 1 upon 780 nanometer will be around 12,000, will be around, yeah, 12,820 centimeter inverse. What if I give you this to you as the relation? Then you will, like, since the relation is E is equal to HC in, sorry, it will be HC nu bar. So it will be like E3 is equals to E1 plus E2, and therefore you will write HC nu 3 bar will be equal to HC nu 2 bar plus HC nu 1 bar, and therefore the total will be like these three will be cancelled, and therefore you will directly get the relation nu 3 bar is equals to nu 2 bar plus nu 1 bar. So therefore in terms of wave number, what will happen, you can directly add the or subtract the values if you want to do the calculation. So this is quite easy in case of wave number, but in wavelength you have to take the reciprocal. And do not, like, this is an essential step, because normally if you calculate the otherwise, if you go to direct mathematics, simple mathematics, you may commit a mistake in this problem. And generally it's an easy one, so I prefer there should not be any, like, confusion or doubt in this question or how to solve this question. Now one more thing which I wanted to discuss in this question was, in what range does this light lie? Like, if you have added 490 nanometer, as you we know 490 nanometer of light will lie in what range? Yeah. So this 490 nanometer, something has happened with the pointer. Yeah. So if you talk about this 490 nanometer of light, this will lie in the visible range. Okay. And 800, so it will lie in somewhere in the higher range, because the visible range is only till the 780 nanometers some more. So if you add these up, you get somewhere in the 303 nanometer, and what this range will be, definitely this range will be UV range. Got it? So, summing up a range of visible or IR, you may be given a question, in which range does the corresponding wavelength or does the corresponding light lie? In which, or which range does it belong to? So then your answer will be definitely that it lies in the UV range. Okay. Now, with this, we'll go to the second question, and we'll be solving. If we have more time, then we'll be solving these questions again, because maybe numericals are the questions which we need to practice. So, the second question is, which of the following factors does not affect the performance of a femtosecond optical gating spectrometer? So, first of all, for solving all these questions, I'll give you a brief description of what are the things that were discussed about femtosecond optical gating spectrometer, so that we get a revision, a quick revision of what was taught to you in the lectures, and therefore each of these questions you can easily solve them. Okay, so. Here is a figure of up conversion spectrometer. So for as usual for a spectrometer, it starts with a light source. So here, actually, this figure I have taken from the lectures itself, so that we do not have any confusion. Because, and second thing, all these annotation and this figure is quite clear with all the descriptions. So it would be very easy to for me to describe using this figure itself. Now, first, this is the light source, which is a titanium sapphire laser, which gives a 100 femtosecond pulse with 80 megahertz frequency, and the frequency of the laser source is, or sorry, the wavelength of the laser source is 800 nanometer. Now, so it gives 800 nanometer wavelength of light, and 100 femtosecond pulse of it. As you like in the earlier discussion, we had discussed about what is the value of femtosecond. So for a picosecond, it is 10 to the power minus 12 of a second, and minus 12 of a second, that is picosecond. And just a second. So femtosecond is 10 to the power minus 15 part of a second. Okay. Now, actually, this scale of resolution we do not get in the normal experiments, and therefore, for a better time resolution, they have always preferred to use this up conversion spectrometer, or you can say this is fluorescence optical gating, uh, which is only if the only purpose for this to be used is because it has a better time resolution. Now, you take a titanium sapphire laser which has a 100 femtosecond pulse. Now, this 800 nanometer of light, as you can say, this lies normally in the IR range, or say in the visible range of the red region. So here they have labeled it with a red color. First of all, from the light source, this goes to this reflecting mirror M1. Now, from this reflecting mirror, it is reflected at this particular angle to mirror 2, and from this mirror 2, which is labeled as M2, this light will go to one converging lens. Okay, so what does a titanium sapphire laser the pulse of light which a titanium sapphire laser gives with respect to time, its intensity is like in the form of this short pulse. Okay, so this short pulse, it is polarized, and in a particular direction, say this. Okay, and then it moves through this lens. After moving through this lens, here is called something called written BBO and SHG. What do these two terms denote? Now, BBO is denoted for beta barium borate. So BBO, basically this BBO, beta barium borate, it is a second harmonic. It is an inorganic material first of all, and it is an SHG material. What is this SHG? SHG is second harmonic generation material. Okay. Now, what is this SHG? Second harmonic. Now, as you can say, second is for something second order, and harmonics is always related to you can say uh, the frequency of the light beam. Now, what does it do is, the wavelength of light, suppose it is given, okay, since we know here an 800 nanometer of light source it is, when it passes through this SHG material, the frequency gets doubled the frequency. Okay, so the final frequency of the light beam when it passes through this second harmonic generation material, it becomes twice. And therefore from red, if you say the wavelength, in terms of wavelength, since frequency is getting doubled in this case, the wavelength has an inverse relation with that of frequency, and therefore the lambda will become half of its original value, and its value will turn to be 800 by 2, and therefore equal to 400 nanometer. Now, isn't it interesting, because these are the materials itself which have which convert this the wavelength of a higher wavelength of a higher value to a lower value, or you can say a frequency of a lower value to a higher value. Suppose this is useful, why? Because if you have a light source of say 1040 nanometer, or one, or say 1020 nanometer, or in other language 1040, okay, 1040 nanometer light source only you have, and you need something which is in the range of say 400 to 500, okay. So you need the light wave, which is light beam, which has a wavelength of 400 to 500. So what you need to do all is just keep an SHG material in the way, and this thing will be reduced to the half. So from 1040, you will get the wavelength of light that will be somewhere 520 nanometer. Exactly 520 nanometer in the other words. And this makes the process easy. You need not to change your entire source. You just need to keep a new material, that is SHG material, in its way, so that directly you get this conversion happen. If we get like in the few next few steps, I'll be like, it will be better if I just give a recap of how it was explained that the frequency doubling, or you can say this yeah, exactly, the frequency doubling takes place, okay. And from here, so back to the process of this back to the entire diagram of this spectrometer. From here, after conversion, this 800 nanometer of light, it converts to somewhere of 400 nanometer, okay, right now 400 nanometer. Now from 400 nanometer, it goes somewhere to the L2. From L2 again, it again gets converged. Now as you can see, not all the light which is given to this SHG material that gets converted from 800 to 400. There is some amount of light which is left, which has an intensity, or so, or okay, which has a wavelength of 800 nanometers. So basically, out of SHG, we get a mixture of light. One will be of 800 nanometer also, and the other will be of 400 nanometer. Now, how to separate them? In order to separate them, we pass them through this DM. What is this DM? This DM is uh, dichroic beam splitter. Okay. So, what does this dichroic beam splitter stand for? This dichroic beam splitter, denoted by DM, it separates the two lights. First of all, the initial source of light, which is red of 800 nanometer, yeah, which is of 800 nanometer. This this gets transmitted and gets reflected to this mirror M3, okay, through this mirror M3. And the second light source, and the second light beam, which was converted to 400 nanometer, it gets passed from here, it gets reflected from the dichroic beam splitter. So basically, this dichroic beam splitter transmits the light beam of the source, and reflects the light beam which has come from the second harmonic generation. So this thing happens. What is this? This is dichroic beam splitter. Okay. Then after this reflected light then pass through this ray of filters also. So this ND denotes the neutral density filter. Now what does this neutral density filter do? the wavelength of light which you got, or the intensity of the light that was from a pulse and that too from a laser, had a very high intensity. Now if you supply, or if you incident this same intensity of light to your sample, there is a chance that this much intensity may ruin your sample, or it may also affect the lenses on the way. So, in order to reduce the intensity so that the sample does not get affected or burned, or we do not get any change in the readings, these neutral density filters, these just reduce the frequency. That is, from a higher intensity, they convert it to a lower intensity. Here, this bigger letter I have written to denote the higher intensity, and a smaller letter I to denote a lower intensity. After passing through this neutral density filter, there is something which they called as a barricade, which is on the way, and from there through this entire system, again this light passes through M5. This is the mirror 5, and from mirror 5 again it is reflected to lens 3. Again, since we know that the light is passing through a long way, it may happen that it is more spread. So in order to convert this light, there is another lens L3, so that the light which is incident on the sample, it is quite it is quite like focused on the sample. Okay, so this focused light, when it incidents, or when our sample, which is a fluorescent sample, which is subjected with this source of light, it emits fluorescence. Now what has happened initially was the 800 nanometer of light, which has changed to 400 nanometer, and the 800 nanometer was filtered out. It has a different way through which it will again reach the L6 also. Also, what has happened? This through the dichroic beam splitter, this our what the required was the 400 nanometer of light. It passes through the system. It goes through M5. It is reflected through L3, and in the form of a focused beam, it comes onto the sample. After the sample, it passes through the lens port. Again, since the this is a straight way. Now, unlike the fluorescent spectrophotometer, where if this is the incident light on the sample, we do not keep the detector here. We keep the detector which is perpendicular to it somewhere here, so that only the light which is the fluorescent light comes on is going goes to the detector, and the other one, the incident light, is does not come to detector, because other way, if the incident light comes to the detector itself, will not get a proper reading. So therefore, uh, but in this case, like, here we are saved from that mistake. But in this case, when you see, when the sample passes through this lens, and from the lens it passes through this filter. Yeah. So when, as you see, the detector is right away here, and the lens is here, you will get a mixture of two beams, the one that is incident and the one that is the fluorescent. Now you need to separate these two. Why? Because you do not need the blue one. So therefore, you again keep a filter here. You again keep a filter here which filters out this beam and therefore passes out the other. And thus, this filter F2, which separates this beam from this green beam, is called the long pass filter. What is it? Sorry, it is called long pass filter. Why is it called long pass filter? Because it allow now naturally, if you incident some wavelength of light, say A, or you can say I give it a value of, on the scale of 100, I give it a value of 100. What you get after the fluorescence, that is definitely not 100, that is in the range of 40 or 50 or 60. Okay, so definitely its wavelength is going to be longer than the one. Now you need to pass this longer wavelength, and this filter has to block this shorter wavelength. Okay, so thus, this long pass filter allows the long wavelength to pass as the name suggests, and therefore this green passes through it. It is converged by a mirror, where again the light of this, the red, where again this 800 nanometer source light which we had collected, this goes through this entire system of mirrors and again pass through this. This is something which we had discussed in the previous week, that is the retro reflector, and we had also solved the questions related to this. Pass through the mirror 6, mirror 7, and then again a BBO. Now this SFG, BBO stands again for the beta barium borate, but this SFG is some frequency generation, where somewhere this omega 1 and omega 2, which are the frequencies of these respective light beams, these merge. Okay, and therefore these merge and again are merged by this SFG, and meanwhile what the work this lens does is to converge the two at a single point in this SFG material, and therefore these generate a frequency which is omega 1 plus omega 2, which then passes through this slit, and after that they pass through a filter. Now from this filter again what happens is omega 1 plus omega 2. So here comes the question which we solved at first. These are the two, some frequency generation, where the two frequency add up. These two frequencies are omega 1 and omega 2 respectively. Now what you do is, generally the value of the because as we solved in the previous question, yeah, so the value of omega 1 and omega 2 is naturally less, like the value of wavelength or the frequency is still higher in both. So, here we again keep a filter. Now, since the value of omega 3 will be greater than omega 1 plus omega 2, okay, or so what do you need to pass in terms of wavelength? You need to pass a shorter wavelength, okay. So again, you keep a filter which is a short pass filter. Okay. So here the F3 which is used, this is a short pass filter which allows the shorter wavelength or the higher frequency of light to pass, so that it goes to the monochromator, to the detector, and it does not allow these omega 1 and omega 2 which had come through a straight way to the slit to pass and therefore be recorded, because if this, instead of this omega 3, omega 1 and omega 2, these are recorded, you would get a good plot, a good decay curve which you would get in the case. Therefore the use of this filter F3, which is a short pass filter, is necessary in order to pass the light which is of shorter wavelength and that is of higher frequency. So this is was a very short summary. Although at the some point of time, we'll again need the discussion about each element in this entire instrument, where I'll be giving like there with the questions. Along with the questions, I'll be discussing some features of each of these, so that uh, like we are clear with all the things. Now, so coming back to the question 2, the question was, which of the following factors does not affect the performance of a femtosecond optical gating spectrometer? Yeah. So, first, the factors that does not affect the performance. First is time response of the detector. Second is non-horizontal gate beam. Third is instability of the laser, and the fourth is orientation of wave plate in the path of laser. Okay, so hi Adrija, I suppose you are a bit late today in joining the session, although we are not too much like, although we have not covered much of the questions, only one question has got completed yet. So, uh, so first of all, in the week 3 module, there was the discussion on this femtosecond optical gating spectrometer fog, which is called FOG. So, The factors that do not affect the performance is, first, if you talk about the non-horizontal gate beam. So here in this instrument, what I talked is the what is the gate beam. So first of all, in this entire setup, this the longer wavelength of light, which is the source light, which is not affected by any of the, like, which remains constant throughout.
Hello.
Sorry, did you say something?
Yeah, yeah. I cannot see your presentation.
Oh, you cannot.
Yeah. No, I cannot see.
Sorry.
I cannot see your presentation.
Oh, okay, 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 okay. Just a second. Thank you, thank you.
Yeah.
Just a second. Oh, I'm a bit sorry because I forgot to share the screen with you.
Yeah.
Anyways, you
No
are the
problem.
first one to join, so you did not miss much. Yeah, now is it visible now?
Yeah. Now it is visible.
Okay. Thanks, Adrija.
Welcome.
Yeah. So the question was, which of the following factors does not affect the performance of a femtosecond optical gating spectrometer? So here, first of all, the thing was non-horizontal gate beam. So what is gate beam is? Gate beam is the one that passes the. Oh, okay, just a second. Yeah. So gate beam is the one, the initial source of light that is of 800 nanometer that is filtered out by this dichroic beam splitter. This is this gate beam. Okay. So this gate beam, why did they say we need a non-horizontal gate beam? So this non-horizontal gate beam, why? Because if you see here carefully, these two beams are merging up through converging through this lens to here. Now suppose these two are coming together. Now since for them to merge, there should be like their position should be like one over the other. Suppose you keep it in a way that it is non-horizontal or a bit deviated, these two beams will not merge and will have some sort of difference. They will have some sort of part difference in them. So in order to prevent this, you should have a non-horizontal beam. So first of all, this option is eliminated. A non a no, like this affects the performance in all. There should be a horizontal beam. That should not be a not non-horizontal beam, because otherwise if it is not totally horizontal, it would affect our performance. Okay. The second is instability of a laser. Again, this entire femtosecond thing we are doing only on the basis of this our laser source. Now suppose it gets shut down, there will be nothing what you will get in the what the detector will detect, and how you will get the measurement. So for a good measurement, for the accuracy of the instrument, your laser should be stable, quite stable during the entire process. Okay. I think, Adrija, you missed the starting part. Okay, so within a time of 5 minutes, if we get enough time, or if we are left with time, I'll explain you this entire thing, spectrometer, which I discussed. That is a quick revision of what we have discussed in this week three. Okay, so that that gets revised for you now.
Yeah.
Okay. So first is instability of laser. That should not be the case. If you are working with fog, the laser should be quite stable. Okay. So the factors that affect the performance are this and this. These two affect the performance of laser. The third is orientation of wave plate in the path of laser. So uh, what is this? See, uh, the orientation of each of these things in the path of laser, if it is disturbed to a bit extent, then again it will affect the what we can say is the intensity of the light, and in all the entire process through which this detection is going on. So, in order to avoid this or this as an error, what do we need is the orientation of wave plate in the path of laser. That should be also in a proper, like the orientation should be proper. Got it? So, if you can understand what point I am coming to, this is the thing. You see time response of the detector. Okay, so here there is a pulse laser which is coming up to you through here to this sample. You get a continuous light through when it in the form of fluorescence when it passes through this sample, which is in the form of this decay curve, something like this, and then it is detected by the photomultiplier tube, which is the detector. Now this entire process, if you run this same setup for a time of say 1 second, 5 second, 10 seconds, whatever the time you need, this time response of this detector will the factor which will not affect the entire working of the instrument. Okay, or will not affect the performance of this spectrometer. Even a simple detector you can use in the case of spectrometer, because what it has to record is just the change in the frequency. Okay, so how this frequency is recorded and how the value comes, that I'll discuss on a blank page so that it is more clear to you, because this page is a bit scribbled. But what I want to say is this time response of the detector is one of the factors which does not affect the performance anyways, because these three things are directly affected to the instrumentation of of our entire spectrometer. If any of these things get hampered or are not working in a proper way, your reading will not be better. Like, only this detector is the thing like which does not affect the performance of this spectrum. Okay, now with this we'll go to the second question, sorry, the third question, which is function of a dichroic beam splitter in the setup discussed is to separate first excitation light from the fluorescence light, fundamental from the second harmonic, some frequency from the fluorescence, and some frequency from the fundamental. Yeah. So here, as see, first of all, this dichroic beam splitter is in this diagram. Let me clear this in this picture, not a diagram. Okay, yeah, I think it will not be done. So basically, this dm, something which is denoted with this dm, is dichroic beam splitter. Okay, now since we cannot draw more on this page, I'll draw using the pen on this page itself. Okay, so this is somewhere the light source. Okay, this is the titanium sapphire laser. From this to through a systems of mirror, the light gets reflected and goes straight. From there, it goes through an SHG crystal, second harmonic generation crystal, where if it has a frequency of omega, this omega is like it emits the frequency which is just the double of it. say 2 omega. Okay, the second harmonic generation is the crystal which is responsible for the frequency doubling thing. Suppose you give it a light of although it may be wrong, I should discuss this in terms of frequency only. So I'll just say that suppose you are giving it a frequency of say uh, okay, uh, what if I tell you the value of frequency is sorry, the value of wavelength is 800. Okay, so just try to convert it into the value of frequency. So it will be 3 into 10 to the power 8 meter per second whole upon 800 nanometer. So 800 nanometer, so into 10 to the power minus 9 meter. So this this will go up. Okay, so it will be 10 to the power 17, and 3 divided by 800, so it will be 3 divided by 800, so it will be 3.75 into 10 to the power minus 3. So 3.75 into 10 to the power minus 3, and meter will be cancelled with meter and it will come to be seconds. Okay, so it will be 3.75 into 10 to the power 14 seconds. Sorry, second inverse. Yeah, second inverse. And okay, you can just say it is, yeah. So this is somewhat the somewhere the frequency. So yeah, the frequency will be double. It will be the double of some this value, and then we pass it through this SHG. We pass it through a lens, converging lens, and then we pass it through this DM, or you called it to be a dichroic beam splitter. Now, what I want to say is earlier also I explained, when the light comes from a light source that has a frequency omega. From the SHG material, it is converted to 2 omega. But what we see by what we study theoretically, practically this is not the case. Like, if you, what you get as the resultant is the mixture of omega also and 2 omega also. Now in order to get the exact thing, you need only one of those. What you converted, you need only 2 omega. This omega is not necessary for you at this moment. So what this dichroic beam splitter does, this separates, or you can say this transmits out this. What does it transmit? This transmits out this initial omega, say omega 1, and this reflects out this 2 omega here. Okay, so suppose in this figure what you saw initially was this red light. Okay, when this passed through this second harmonic generation, it is a mixture of blue and red. This blue signifies 2 omega and the red signifies the omega 1, which I denoted here in the sketch which I drawn. So basically this dichroic beam splitter, it passes this, transmits this red or the 800 nanometer of light or a lower frequency light, and reflects the higher frequency of light, so that it can go on to the sample and therefore we can get the fluorescence record. So basically now you can just answer this question: what does the dichroic beam splitter do? Or the dichroic beam splitter is used to separate which of the two, the excitation wavelength from fluorescence light, or the fundamental from the second harmonic, or the some frequency from the fluorescence. Now here there is a bit confusing thing, that is what is this excitation light. So I think, what I think is, here the excitation light which they are talking about is the light which is used to excite the sample. Okay, so suppose this 2 omega is used to excite the sample, which will, the light which we'll get, the new f will be much times slower than that of this 2 omega. Got it? So here this excitation is light is not this light. What they have called here is this fundamental light. So according to me the answer will be fundamental from the second harmonic. Why? Because fundamental is the one that is coming from this light source. It is going through this second harmonic. From the second harmonic we are getting is the second harmonic 2 omega and the fundamental omega. Now what this DM is doing, this is separating this omega and 2 omega. Got it? The third is some frequency and fluorescence. So some frequency and fluorescence is here. Some frequency is this one and the fluorescence is this green one. So this is being separated, or like these two are mixed. Okay. So this is not the answer of our question. The fourth one was some frequency from the fundamental. So some frequency is somewhere here. This is the some frequency and fundamental is the red line. Okay, so these three are already being separated. Okay, so because this fluorescence light and the initial fundamental light, these two are only summing up to give this some frequency of light. Okay, and these two are further separated using this filter, this short pass filter, which we already discussed, but we will discuss in the further questions more. Okay, so the answer for this question is fundamental from second harmonic. I hope you understood the explanation. Is it clear?
Yeah, it is clear.
Sorry.
Yeah, it is clear.
Okay.
Yeah, it is clear.
Yeah. Okay. Thank you. Now next. And is my voice audible to you properly?
Yeah,
Is it loud
yeah, your
enough?
voice is audible.
Okay. Thank you. Now, and now I'll go to the question number 4. Compared to the transmissive mode, the FOG, that is fluorescence optical gating, in the reflection mode has better. What it has better? Light collection, spectral resolution, temporal resolution, or signal to noise ratio. So, first of all, what we discussed here is transmissive mode. Why is it transmissive? Sorry, what we discussed is a transmissive mode. Why? Because here we are using a system of lenses. Okay, this system of lenses, this passes the light through this entire all L1, L2, L3, and so on. And therefore, since light is transmitted through this entire system, through any medium, you can say, because anyway this lens is some medium itself, right? It is made up of some material. Since in this whole case, this whole path, it is transmitted through different materials, it is called the transmissive mode. Got it? Now, what happens in the reflective mode? In the reflection mode, anyway, as the name suggests, reflection should happen. So, here I have a diagram of this. Okay, this diagram also I have taken from uh, our lectures itself. So basically, again, this is a femtosecond laser. So femtosecond laser, that it has, it gives the short pulses that are in the range of femtoseconds, which are highly intense enough, and the titanium sapphire laser source emits the light or the pulse of of wavelength 800 nanometer. Okay, and the what is the lifetime of this pulse? That is 100 femtoseconds. And what is femtoseconds? 10 to the power minus 15 of a second. Is it right, Adrija?
Yeah,
So this light, after in this entire system, we do not use, oh, okay, here we use a lens, but in this entire system, as you can see, we do not use the lenses, we use these parabolic mirrors. Why do we use these parabolic mirrors? These reflect the light. So generally the case is, if the light passes through some medium which transmits, it's like it will take more time, and therefore its resolution time will increase. Suppose for any instrument, you say the resolution time they have mentioned is say 120 femtoseconds, but then if you use this entire transmittive mode and the collection of lenses in the way, yeah, it will reduce to somewhat double or of it or more. Like the resolution time will increase, and therefore your resolution will not be better. So to get that, what you need, this reflection mode is a better way. Okay, So in this case, the light in the same way it passes through SHG material. This is second harmonic generation material again. And what was the second harmonic generation material? I think you missed it. That is a BBO. Okay, that is a BBO crystal, which is it is expanded as beta barium borate. Okay, so this beta barium borate is the second harmonic generation material which doubles the frequency. Now what we have got is 2 omega. Again, this passes through the filter and goes through the sample. To the sample, what it gets is the pure 2 omega frequency. Right now, from this 2 omega frequency, the fluorescence light which is emitted by the sample, it goes through the system of parabolic mirrors. This omega 2, this again passes through this system, unlike the other where unlike the transmissive mode where lenses were used. Here it moves through this parabolic mirror way, and therefore it is reflected to this, and again through this way, and again it moves straight to the BBO, beta barium borate. And what this BBO used to do was working as SFG, some frequency generation material. Unlike this merges or sums up two frequencies which are different from each other. Okay, it sums up omega 1 and omega 2. Unlike here, the case was that was the frequency had the equal value omega plus omega used to give 2 omega. But in this case, omega 1 which comes from here and omega 2 which comes from here, these two are merged to form this. Okay, and this omega 1 plus omega 2, this then passes through a system of slit, and then it goes through a lens, the converging lens. From there it goes to a filter. Now as usual, when you pass this light, this fluorescence light to it, you will not get that a case where you will only get omega 1 plus omega 2. You will get some amount of omega 1 and some amount of omega 2 also along with this. So, for you to get a good reading, to get a good resolution and a clean spectra, you need to cut these out, these two wavelengths. Again, since these two frequencies, or say wavelength, these two frequencies are smaller than these two. Okay, sorry, are greater than these two. This is a smaller frequency. Why? Sorry, this is a higher frequency. Why? Because this is a sum of these two. So this higher frequency is passed, and these two smaller frequencies, these are retained. Okay. So what do you need to pass on is the higher frequency. So okay, but if you talk in terms of wavelength, that will have a shorter wavelength. So that's why you call this filter a short pass filter. What do you call a filter? Short pass filter. Why? Because it passes only the shorter wavelength of light. I think this is a bit confusing because the entire thing we are discussing in terms of frequency, but when it comes to the filter, we are talking it in terms of wavelength. But anyway, since the name, we cannot do anything with this, so we have to do it the way it is. So we call it a short pass filter. Why? Because it allows only to pass the light which is of shorter wavelength. Okay. Now in the reflection mode, as you can say, this transmitting thing is the thing which is eliminated. Light is reflected through this entire case, and therefore the time resolution in this case is far better than the transmissive mode. Okay, so that's why this reflection mode is quite better only in terms of transmissive mode, that the okay, I'll write it here. Time resolution is better. What it is? Time resolution is better. Got it? So, what is it? Time resolution is better. Now, Compared to the transmissive mode, FOG in the reflection mode has better. So options were light collection, spectral resolution, temporal resolution, or signal to light noise ratio. Now see, here time resolution is not given to you. Okay, time resolution, instead there is a term as you see, that is temporal resolution. So, actually, in the scientific terms, if you say something, the resolution is in terms of time. If resolution in terms of time is studied, then it is referred as temporal resolution. Got it? So, in reflection mode, basically this temporal resolution, it is better. Adrija, if you have any doubt, or say I suppose, like in the reflection mode or in this upconversion spectrometer mode, because I suppose like this is the part you had missed, and if has anyone more joined our class? Uh, do you have any doubt in this spectrometer upconversion spectrometer part? Or if you say I can discuss this in a short way so that you can understand, or all your doubts regarding this will be clear if you want.
Yeah, it will be better if you discuss in like shortly.
Yeah, okay. Give me a second.
Yeah, sure.
Okay, so up conversion spectrometer, first of all, starting with the light. First of all, earlier whatever we have discussed, uh, in order, what was the main principle of ours is to study the dynamics of the like some reaction, since most of the reactions whatever we studied on a time scale, those were like seconds, microseconds, milliseconds. Now if for a very shorter time period of time, if you want to resolve the or you want to study the dynamics of any reaction for a shorter, very short time scale, say femtoseconds. Okay, because as if you remember, the fastest process what we saw was in the range of femtoseconds, right? 10 to the power minus 15 or minus 12, it was somewhere. So, if you want to study those fast processes, what are the ways? So, basically, this design of upconversion spectrometer is also one of the techniques which we have evolved in order to study those femtosecond range of processes. Okay, or say in order to get a femtosecond resolution, we this entire design is done. Now why? Because all the devices, the electronic devices which are used in the machines, they are not fast enough. So here the fastest thing that is they have used, that is the light. Okay, since light that has a speed of 10 to the power 8 meter per second order, it is quite large, and therefore, or say it is quite fast. So, using light as a source only, we can study this femtosecond thing. Okay, the processes which are of which are as fast as in the time scale of femtoseconds. So in the upconversion spectrometer, first of all, there is a titanium sapphire laser. Why do we use a laser source? That also we had discussed earlier, because the laser light is highly intense, it is monochromatic, and also it is not collimated, so it is quite focused beam. Okay, so here we use a titanium sapphire laser which has a wavelength of 800 nanometer and gives a pulse of 100 femtoseconds. So this much short pulses it gives. Okay. Now this titanium sapphire laser source of 800 nanometer with a frequency of 80 megahertz, it goes through this. Okay. This light source as 800 nanometer, it generally belongs to visible or say the IR region, right? Now this has very low intensity. This is a low energy light beam generally, and in order to excite a sample, say for fluorescence, you do not need 800 nanometer of light. You need somewhat more than that. So first of all, from the source, when this light goes, it is reflected through the mirror M1. Okay, this mirror M1 reflects this light to M2, and from this M2, this light goes to this L1, this lens 1 system, where this lens, as usual, as you can see, it converges this light beam, and from this light from where this light beam goes to BBO, this is beta barium borate. Okay, this beta barium borate, the second harmonic generation material, it converts the wavelength of it converts the light of frequency omega to 2 omega. And why? Because this is second harmonic generation material. How does it do? That is a different way, that is a different process. But basically, if you want to study is uh, this in a fair words, you can just see this. I'll draw a diagram. Say this is the ground state of any material. Okay, sorry, this is the ground state of any system. You incident it with a light of frequency omega. Immediately it will reach to an excited state, or say it reaches to a virtual excited state, which has a lifetime of zero, which has a lifetime of zero. It reaches to this higher virtual excited state, and without any time lag, only from this virtual excited state it goes to the second highest state, which with the by gaining a second photon of frequency omega. So basically, from the frequency of omega, from the photon of light, that is say 800 nanometer, because here we are studying of 800 nanometer only. From here it goes through this virtual excited state, and from this virtual excited state, by taking yet another photon of light of frequency of the same frequency without any time lag, it reaches to this higher excited state. Now after reaching this excited state, it comes back to the ground state again without going to this virtual state. Now how much energy does it has? It has an energy of omega plus omega. Therefore, in terms of frequency, we can simply add up, and therefore it will emit the frequency that is of 2 omega. Got it? Now, so here in this, okay, in this case, this 2 omega, when it passed through this lens, this has a mixture of the initial 800 nanometer along with the one is 2 omega. Now why this is denoted, this is colored as blue? Because it has a higher frequency. So normally, when since blue has a higher frequency than red, so this is colored as red, this is as blue, the higher frequency. Since this is a mixture, we have to separate it. It passes through a dichroic beam splitter. From the dichroic beam splitter, the fundamental light beam, it is transmitted out. The light beam, which is second harmonic generated, that is reflected through this beam splitter, dichroic beam splitter. It passes through this neutral filter. Now why is this neutral density filter fitted here? Why is this on the way, and what is the purpose? So this neutral density filter, basically it reduces the intensity from this I say higher intensity to a lower intensity. Why? Because This laser, this for sure, this is a laser beam, or like this is a laser light, so it will have a very high intensity. And this much high intensity is not that much necessary for our sample, because if you incident it with such a high intensity of light, it can be damaged. So these neutral density filters, these reduce the intensity. Further, this goes through this barricade sort of barricades, which are used for changing the optical, the rotation, the polarization of the light, and therefore it passes through the mirror 5, it gets reflected, goes to the sample. Okay. Now, what is this? Say from 800, the wavelength is reduced or turned to half of 400 nanometer. Got it? From 400 nanometer, this 400 nanometer of light, this incidence on the sample, and this sample, it emits a light, or since this is the sample which emits fluorescence, uh, we get a different frequency of light again. Suppose it is a 400, that would be definitely of a higher wavelength than this 400. Again, this light beam, the mixture goes through, passes through this L4, which is again a lens, and passes through the filter F2. What does this filter F2 does? Because as usual, you see from the figure, see this is again a mixture of green and blue light. So again, this blue light is filtered out, because what do we want at last is this fluorescent light. This fluorescence light is transmitted, and this the blue light is blocked by this filter. Since the blue light has a shorter the blue light has a shorter wavelength than the green, it is called as the long pass filter. Yeah, right. It is called the long pass filter. Why? Because it allows the long wavelength of light to pass. This omega 2 then again goes through this lens, and meanwhile from here the fundamental beam of light goes through this system. Now again, which this is thing which is to be discussed here is this reflector. Earlier, if you remember, in the previous week, in the week 2, we had discussed what does this retro reflector does. So this retro reflector, basically it is used to change the path difference of the light. Okay, so why is this path difference needed, or the change in the path difference needed? Because like when the light goes through this entire system, in order for these two to converge, there should be zero part difference between the two. And in order to maintain that, because naturally if it comes, there will be a part difference, a little bit of part difference. If you want that the part difference should be zero, you have to change it a bit. And for that purpose, you need something called a retro reflector, which helps to you to do so. This reflector helps you to change the part difference from say 0, 1, 2, 3, 4, so that these two match to each other, and therefore can be like therefore these two can be focused on a single point in the SFG, so that the sum frequencies can be generated as omega 1 and omega 2. So here on these two frequencies, omega 1 and omega 2, will be like summed up, and what you get at last and what is detected by the photomultiplier tube, that will be omega 1 plus omega 2. Okay, now say here I am going to explain on the blank page. Say here, initially what you got as the fundamental frequency, that was a pulse. Okay, so the red one which was denoted in the figure, that is a 100 femtosecond pulse, so it will be like this. Okay, as intensity with respect to time. The second one, since it is a fluorescent light, it will be in the form of decay like this. Okay. Now, naturally, if you if you sum these two up, there may be some part difference. So, if you plot it as intensity with respect to time, say there is some part difference in these two. So, the pulse is up like somewhere here, and your fluorescence decay is somewhere here. So totally what you will get, what will be detected by the PMT, that will be not at all intense, because omega 2 and omega 1, they have a part difference That is quite too much, and therefore the intensity with respect to time what you will get is zero. Okay, again it comes to this place. Okay, so it comes to a place somewhere here, but again there is still some part difference between the two, so you won't get any intensity. If you further move the retro reflector and reduce the path difference, and therefore it comes to this point, you will see that there is some intensity of light you get. Okay, further, like as I'm showing, like there will be a somewhat overlap, further it will increase. So you will get somewhere here at some point of time you will get maximum intensity, and again if it passes on to here to here to here, the intensity will further reduce. Okay, here the value of fundamental frequency or the omega 1 is the one which is constant, which is also called as the gate beam. Okay, but what changes is this fluorescence. Now what you get is in the yet in the form of this decay only, what you got in the earlier experiments. The thing is only that you have summed up these two and you will again get this intensity to time curve. Got it? So this is what you get a decay curve through the this fog experiment, and this is the thing which you can study in order to study any decay process, like what is the lifetime, how much time it takes, what is the resolution, and other things which you can calculate using this. So basically this was the uh, entire short, like in short I had described the whole up conversion spectrometer. Now I'm going to like Adrija, did you is everything clear to you now?
Yeah, it is clear.
Okay. The same way in the up conversion reflection mode, you use the parabolic mirrors instead of the lenses, so that the reflected light beam, since it passes through the lens, does not pass through any material or something, the resolution time of this instrument is greater than that of the transmissive mode. Okay, so yeah, now we come up to the question number 5. The magic angle of polarization is. So magic angle, actually this is something which is more technical, and it is like we'll discuss in it in short and a simpler way. So basically, suppose from the light source, as we had seen, the light was passing through here and here. So this is a polarized light, right? Say this has polarization in this direction. Now, when it passes through the SHG material, the say this SHG, this is SHG material, its polarization changes to a direction that is 90 degree to the original one. Okay, direction of polarization, what does happen to it? It changes to 90 degree. And further, if it moves through different paths, there is change in the angle of the rotation of the polarization and all happens. So in order to prevent this, like what does happen when it passes through, and when it passes through SHG and there is change in the polarization angle, what you get in the reading, there is some rise and fall in the obtained frequency or the obtained polarization. So like the decay what you get, that is some, there is somewhat like rise or fall in the decay process. Okay, in the intensity of the decay process. So in order to avoid that, there is something called the Barrick gate, which we had seen in this figure, this denoted by this. Okay, now this Barrick gate thing, like if you keep this entire system at an angle of, that is 54.7 degrees, then what happens, this like in this polarization, the change due to the rotation, and change due to the rotation in the polarization, that is reduced to zero. Now what I can say all is there, like there is a like change in the, what you call it is, yeah, that is change in the polarization. Okay, that change in the polarization is minimized to zero at this particular angle, and therefore the problems or the deviations from the actual reading which happens because of the rotation in polarization, those are minimized. Okay, rotation in the polarization direction or the direction of polarization, that is minimized at this angle 54.7 degree. Okay, so that is why the magic angle of polarization is 54.7 degree. And that if you see in this instrument, okay, I think that is somewhere here. Yeah, this angle is somewhere at 90 minus 54.7 degree. Like we keep the sample at the angle that is at the magic angle. Okay, there is a, like if you calculate this, that will, the value of, yeah, the value of it, this would be, this angle would be 30.3 degrees, I think. Yeah, 90.0 minus 54.7. So wait a second, this will be 9 minus 4 5. Okay, and yeah, sorry, it is not 30.3, that is 35.3. So if you keep the sample at this 35.3 degrees, then the change in the reading, or that rise and fall in the intensity which is observed due to this change in the rotation pole, like the which happens due to the rotation of the polarization, that is minimized. So magic angle for polarization is 54.7 degrees. Okay. Now we come up to question number 6. Adrija, do you does any one of you have any doubt in this question? The last one, magic angle of polarization.
No, I don't have any doubt.
Yeah. So we come to the question number 6. In 2D, in 2D upconversion experiments, measurement is faster, temporal resolution is better, spectra as well as fluorescence decays are obtained, or the detector is a 2D array. Actually, initially, what about this measurement is faster or the temporal resolution? So, in the 2D upconversion experiment, what happens, you can take, suppose in this instrument, at last what you get is intensity with respect to time. Say this you have plotted as a function of, like, yeah, say this you have plotted as a function of, say this is the time of 0 1 0, sorry, 0 0.1 0.2, such on the scale of time. Okay, and this is, say, wave number. Okay, so you will get somewhat a plot, like at this point the intensity was this, at this time the intensity has wave number has reduced to this, and say this type of plot you got. Okay, now second, you can plot this in yet another way, that what you have taken is, like here you have taken the wave, here you have taken the wave number, and here you have taken the time. So at time 0 the intensity is 0. Now with the time, the intensity, or say the wave number, had increased to this much maximum value, and then further it got decreased. So you can say that you can measure both. So like if you see, this is the like this sounds similar to that, the spectra as well as the fluorescence decays, that both can be uh, observed. So in the 2D upconversion experiment, first of all, Yeah, measurement can be faster or slower. That depends on the detection time, whatever you take. Suppose you run the detector for a time of 5 seconds, you can run for it for a 10 seconds and take the reading, like how much the fluorescence, how much the intensity has increased or reduced, and how much it went through, and okay, and how much times you take the reading. The same experiment, how many times you can do for a period of 5 seconds or for a 10 period of 10 seconds, whatever. And temporal resolution, anyway, that is better. So first of all, if you talk about the 2D upconversion experiments, you get the details of the spectra and fluorescence decays both. So this will be your answer. And talking about the detectors, actually in the upconversion experiments, you do not need a very high, like highly sensitive or a very efficient detector. A simple 1D array of detector can also work. So only the simple detectors like photomultiplier tubes can also work in case of the upconversion spectrometer. Okay. So basically the simple detectors also can work because there is no time resolution, like because there is no time barrier. In this case you do not need very fast detection, so only the simple detectors can also be used for the measurement. Okay. So actually this can be the option, but in this case they are particularly talking about what kind of measurements or what kind of things you can obtain from the experiment by performing the experiment. That is why the this option is not correct and the third option is correct. Got it? Is my point clear to you?
Yeah, it is clear.
Yeah, okay. So, with this, we'll come to the question number 7. Among the following, measurement that has best time resolution is. So, first is stopped flow fluorescence. Uh, so, the second is TCSPC. The third one is measurement by streak camera, and the fourth one is fog. So, first of all, so far we have not discussed stop flow fluorescence. We have discussed TCSPC, measurement by streak camera, and fog. So basically, in the streak camera, there is nothing about the time resolution, but compared to the TCSPC and fog, the time resolution is still faster in case of FOG fog. What does this fog stand for, Adrija? Can do you have the answer? Actually, I repeated this same. Okay, so fog stands for fluorescence, optical, gating. Okay, and if you are confused with the name, actually this up conversion spectrometer and the fog both are the same thing. Okay, why is this up conversion called? Uh, do you have any idea why is this called the up conversion thing? What does this up conversion mean? Hello, hello.
Yeah, yeah.
Yeah, do you have any idea what does this up conversion mean?
Can you repeat the question?
Actually, what I asked is, what does this up conversion mean? In this, why is this called up conversion spectrometer? Yeah, so I think like it is. I have also not mentioned this. Why is this terminology given to it? So, up conversion, why is the name given to it? See, if you see right from the starting, this frequency, light of frequency omega is converted to 2 omega, right? From this to omega, again when you pass this light through a sample, it has a frequency, like it emits a light which has still a higher wavelength than that, and therefore, sorry, yeah, this goes to, like this has a frequency of omega 2, say. And initially, what was the omega that is considered here as omega 1? It again goes to this lens, and these two are summed up. So, in all, this omega 2 is up converted with the help of this omega 1, and therefore, what we get is the sum of omega 1 and omega 2. Got it? So, in all, what we get is the sum. Okay. Up conversion means something greater than the initial value. Suppose you have 10, you have changed it to 100. Okay. That is the thing what this up conversion means. Got it?
Yeah.
So this subconversion is like, uh, because initially for any fluorescence decay curve, what we study is the raw of this fluorescence data. Okay, or the omega 2 we study. But here what we are doing is we are adding up this omega 1 and omega 2 to give some omega 3 which we are studying. Got it? Is my point clear?
Yeah. It's clear.
Okay, thanks. So here also this up conversion was of the same meaning. And 2D, why is it? Because you can do two sorts of measurements, like in other way round. Like you can do of wave number with time, and with changing time you can set a constant, like a range of the wave number, and with that as the time passes, what is like how much you get each. Okay, so yeah. And since each of the instrument has its own pros and cons, first of all, TCS PC has far better, like the spectra what you get is far better in case of TCS PC than in the case of like in TCS PC, which you talk about, like if the value of chi-square is in the range of near to 1, okay, or near or close to 1, you will get somewhere like a straight line, okay, and not any disturbance. The signal would be quite clear. But in case of fog and light, you do not get a signal that is quite nice. You get somewhere like this spots which are like these points which are joined to each other like this. Yeah, so it is not very that much clear. Like the signal is not that much clear as you get in TCS PC. But if you talk about the time resolution, in case of fog, the time resolution is quite better than TCS PC. Got it? So for each instrument, there are some good points and bad points as well. This we come to the question number 8, that is compared to the transmissive mode. Okay, I think this question has got repeated again. Yeah. So we'll come to question number 9. A long pass filter transmits lambda A and reflects lambda B. Which of the following relations are correct? Actually, that is why I focused on the name long pass filter and short pass filter. Actually, long pass. If something is passed along it, okay, the something that this filter allows to pass through. So long, it is studied in terms of wavelength, okay, and short also in terms of wavelength. Okay, so the property of this filter, if we want to study, that is in terms of wavelength. Okay, if it is a long pass filter, it allows longer wavelength and filters out shorter wavelength. Okay, so suppose here they have asked that the long pass filter transmits. Suppose you say this is a filter. Okay, this is a filter F. Now it transmits. Transmit, what does it mean? Like suppose it has lambda A plus lambda B. Okay. Now this, what does this filter do? It transmits lambda A and reflects lambda B. Okay, actually this is not visible here. So it reflects out lambda B. So transmits means it has this has gone somewhere or it is absorbed. This we do not want, and this we want. It reflects it. Now, so basically, if these two are separated from each other, definitely they are not equal to, because filters are the one which are specific to a definite range. Okay, like they allow some range of wavelength to pass and do not allow or block the other range of wavelength to pass. So if it is transmitting the lambda A, definitely the lambda A would be greater than lambda B. Okay, I think I told a bit wrong. First of all, if it is transmitting it, that means it is allowing the lambda A to pass, and the lambda B, it is reflecting it somewhere that it does not allow the lambda B to pass through it. If it is allowing the lambda A to pass, that means lambda A, like the light beam A has a longer wavelength than light beam B. So actually, if you notice, there are two types of these points. So these square points, they denote that there are more than one correct option for the same question. So here lambda A is greater than lambda B. So first of all, this will be our answer. The second thing, what is it? Definitely lambda and lambda b are not equal to each other, because in case lambda and lambda b would be equal to each other, none of them would be filtered out. Okay, so that is why this relation is not at all correct. Lambda is equal to lambda b. Or the second thing, what we concluded is, a since it is a long pass filter and it has allowed the lambda a to pass through it, definitely the lambda a is the longer one. So lambda is longer than lambda b. The second thing is, obviously this option then becomes wrong. The last option is lambda a is not equal to lambda b. So definitely this option is also correct in this case, because they are not equal. Okay, so sometimes you will get these multiple selective questions where you can get more than one options correct for the same question, and you need to be careful while selecting the options, because although this is not a direct answer for this question, but this is still an answer for this question. Okay, so now we'll go to the next question. That is question number 10. Upon increasing the integration time of the fog experiment, the total, what happens? Total signal increases, average signal increases, signal to noise ratio becomes better, or the measurements is faster. Okay, actually the integration time means that the, like what you get is the sum of the total small experiments which are going on. Suppose you got one reading at 303, the other at 304, the other at 310, the other at 38. So this will be the average of what you get the final after integration. That will be like the sum of all these. Okay, so therefore if you increase the integration time, the average signal increases. Okay, and then second thing is, since you increase the integration time, you will you will come up with some value which is in the middle of these, and you will get a better signal and with a better resolution also. So the signal to noise ratio also improves if you increase the integration time of a fog experiment. And as I said earlier, for this fog experiment, you can take the time to be of variable. You can take it to be 2 seconds, You can take it to be uh, 10 milliseconds. You can take it to be 5 seconds even, or you can run it up to 10 seconds. That is up to you. Okay. And the like although there is some, because you cannot run the same experiment for a longer period of time, you need some optimum time for which you some optimum integration time. So you decide somewhere in between, between this range, not to not much more time, not much less time, so that you get a better signal which has signal to noise ratio better. Signal to noise ratio means you have a clear, smooth signal with very less noise. Suppose your signal is in this way, or you can say in this way, which is a better one. Okay, so definitely this is a better one compared to this has more noise. Okay, so upon integration time, first of all the signal to noise ratio becomes better, and second thing is the sorry, not the average. Okay, actually the total signal increases. Okay. uh, Sorry, this is a mistake. Actually this is not the average signal, total signal was the answer. Is there any doubt in these two questions, the question 9 and question number 10?
No, it is clear.
Okay. Yeah, so we come with this, we come to question number 11. In an intensified CCD, the microchannel plate act as. Okay, so actually this part of the none of the questions had come related to this part till now. So in short, I'll say is, in the intensified CCD, just a second. What is this in ICCD? First of all, what is the CCD? CCD is charge coupled. Do you know what is this? CCD, this is a detector. What is the full form? Do you know?
Charge couple device.
Yeah. So I stands for intensified. So in short, it is called ICCD. It is intensified charge coupled device. Okay. And what happens is, there is an array of small channels in it. Okay, in charge coupled device. Then there is a photo like cathode, and from here the photo electrons, they generate a current or the voltage here, and which goes on to the different points in this array of points, and therefore you measure the photo current as a function and generate a signal. Okay. Now the what does this micro channel plate does? Okay, suppose now this micro channel plate, assume it in the form of a pipe. Now when a single photon, say a single photon strikes on this, this has a system, say like this, or yeah. So in this system, suppose you incident one photon in this plate, microchannel plate. Then since it has a smaller diameter, this again gets reflected within the plate itself to somewhere here, say from here it goes to here. Okay, but meanwhile, while it is incident on this point, because of its high intensity, there are more number of electrons generated or emitted from this point. Say from this one, at this point, around five of these, uh, say, five electrons are generated, five photoelectrons are generated. Okay, now again these electrons within the same, this within the same system, it again reflects here, sorry, it again strikes here, and at this point, suppose these five, they are again multiplied to 10. Okay, multiplied to two times. So they say, you will say 10 electrons are generated. And again, through this entire channel by continuous reflections, what happens is, like through a single photon, a number of times, say 1,000 times or more than, even more than that, photoelectrons are generated. Okay. Now, in all, what comes to the detector is a highly intensified signal. Generally, from the single photon, you have generated thousands of photoelectrons, and these thousands of photoelectrons then generate the current in this CCD detector. Okay. So basically, this microchannel plate, which has a smaller diameter, and which is connected, or which is also connected to this CCD, this microchannel plate act as the intensifier. Okay, so it acts as an intensifier along with this detector, which is responsible for intensifying the signal. Okay, why? Because anyway, through this high intensity single photon, it is able to generate thousands of photoelectrons. Got it? Which are the ones who generate the photocurrent in this CCD. Got it? So, is there any doubt in this MCP working? Because MCP is a small plate which help, because of the single photon, highly, through this surface only number of photoelectrons are generated. That is it. That is, in simple words, that is the only thing that happens. And therefore, because of the continuous reflections within the same area, you can generate hundreds or thousands of photoelectrons, which therefore intensify the signal. Got my point? Is this thing clear to you about intensifier?
Yeah, it is clear.
Oh, okay. Now we come to the next question, that is question number 12. In the streak camera, the streak is due to, okay, spectral dispersion, dispersion in time, difference in the arrival time of photoelectrons, or difference in the speed of light of different colors. Okay. So first of all, suppose, like say, as it was explained, what is a streak camera actually? See, this say you applied voltage, okay, and some of the say photoelectrons are generated. Okay, now what happens is, initially, say less number of photoelectrons will be generated, but with the, as in the middle of time, a lot of photoelectrons will be generated. Okay, as you apply the voltage, and further it will be less. Now that happens because you apply a pulsed, say you apply a square pulsed voltage, like say you at this point of time you do not apply, there is a delay, but at this point of time suddenly you apply a voltage, you run it for some particular range of time, and then again you turn it to zero, you apply a square pulse wave voltage. Okay, so initially there will be less number, then again it will increase, and then it will reach a maximum. Okay, from these photoelectrons, when they pass through a slit, like this is what happens in a streak camera, then it passes through a lens, and from this lens there is a photo cathode and anode. Okay, this is a photo anode, and this passes through this entire system. So okay, I'll rub this thing. Yeah, so from, wait a second. Yeah, so say this is a slit, okay, which passes, say initially the first one to come will be the one which has come in the least time. Okay, or say, suppose these are the three range I take, 3, 2, 1. 3 are the one who, which are the fastest. Okay, the faster it comes, the faster it goes through the slit, the faster it passes through the lens, the faster it comes to this photocathode, and the faster it gives the signal. Okay, So here it again generates some a set of photoelectrons. So initially this will be the one which will generate this much photons. Suppose the 3 has an intensity, say these are a count in a count of 200, this is in a count of 400, and this is in a count of only 100. So say if these are the 200 number of photons, or it will generate somewhat relatable number of photoelectrons. Then the two which will arrive a bit late, say this was 3, this was 2, this was 1, with the two electrons which will arrive a bit late, this but these are more in count, so these will still generate more number of electrons, but they generate a bit later. Then further, the last ones are the one which come at the last, but and their intensity is only 100. So they'll further generate more or less electrons. So this is the way of the signal. And further, this signal goes to the detector thing, that array of detectors which are detected. Okay. So here is a some called a phosphor screen, which generates the spots and vertical and horizontal lines. Okay, from here you on this phosphor screen, because of this signal you will get spots which are used like which form the display. Okay, so basically this streak camera is something which is used for the imaging thing. Suppose using these photoelectrons only you want to generate an image of your sample, so using this streak camera only you can generate the image, okay, using this phosphor. So the streak, what is this streak? Now suppose it has come through this, passed through this lens, okay, sorry, passed through this photocathode. What happens is, say let's say this is the voltage, okay, so this is the voltage versus time thing. So the amount of voltage versus time for these photoelectrons, you will get an ogive, okay. And this and the other thing is, say these will be deviated at a different angle when they pass through this. So somewhere here will be the, like, uh, sorry. So basically here what you will get the streak is in the form of, say, this lines, because the actually this is a long like in between you study the you apply an oscillating voltage, because of which you get the horizontal and vertical line. So this is a long instrument which has further different things along with it. So basically at last you get these long vertical or horizontal streaks or the lines. And why are these different? Why do you get these different streaks? That is due to say the difference in the arrival time of photoelectrons. Okay, suppose here you get a streak. So suppose you apply a voltage like an oscillating voltage which increases like this and decreases like this. Now when the 3 has come, you have applied a positive voltage, so it has deviated to this point. So this is for the 3. Now suppose the time when the 2 second type of photo electrons come, the voltage is 0, so that is not deviated at all. Okay, so this is for 2. And the third one, where by the time the first category of photoelectrons come, the intensity has reached to negative. So you these are deviated in this way, and therefore these are the things you called as the streak. And thus they you get 3 different streaks, because that there is some difference in their arrival time, and when they arrive, the voltage, since it is an oscillating voltage, that has different values, and therefore you get 3 different streaks, not a single one. Okay, so basically, in all, I'll conclude that initially there is some pulse source of voltage which generates photoelectrons. When you pass it through the photocathode, further the different photoelectrons which are generated from the same, since there is an applied voltage across it, you will get three different streaks. You will get different streaks depending on the applied voltage or depending upon the value of the voltage in the oscillating field. Okay, so this is the answer for this question. Since the time is quite up, there are two remaining questions which okay, this is the one which we can still discuss. That is, the liquid sample in the fog experiments are rotated. Why? Because liquid, like, suppose here, for the more detail, here we'll look at this diagram talking about this sample thing. This sample can be a solid or a liquid. Okay, now in case of the solid sample, since this light is quite intense and we do not want this light to be focused on a single spot, because anyway if you work with a laser and you focus the laser on a single spot, and your sample will be destroyed because the laser has quite high intensity. So, in case of solid sample, what you do is the laser light, it passes through a way like this. Okay, it passes like this. Okay, like up and down. This is called ramping. Okay, now in case of liquid sample, if you have a liquid sample, what do you do is, for a proper illumination on the sample, you fix it on something which is rotating. So this entire sample holder, it rotates in all the directions. Okay, it rotates in all the directions so that the sample gets illuminated from all the sides. Okay, so this is the conclusion. Like, for the answer for this question will be, the liquid samples are rotated in a fog experiment. Why they are rotated? To prevent precipitation, to minimize the time damage, or to stop the evaporation of solvent, or to maintain uniform concentration. So first of all, as in the solid we do ramping, in case of liquid we rotate the sample. Okay, we rotate the sample, and there are two reasons for it. The first is for proper illumination along all the sides, and second thing is, the actually this is the most important thing, to minimize the damage on the sample. Okay, to minimize that damage on the sample, uh, you rotate the liquid samples. So with this, we conclude for today. Like, if you have any doubt, Adrija, we can give a few more minutes.
No doubt is there.
Hello.
No doubt is there.
Yeah. Okay. Uh, okay. Thank you so much for this. Thank you so much for attending the session.
Thank you.